right, thank you guys so much for coming out. I know it's 7 p.m. on a Wednesday, and I'm sure you had long days and might be hungry, so what I can promise is we'll show you lots of pictures, and by the end of tonight, you'll be really excited to go and try generative AI. So, hi everyone, my name is Aditya Bindal. I'm with the product team at AWS AI, and I have my co-presenters here with me, Yongjun and Wongsuk. Would you like to introduce yourself?
Oh, okay. Yeah. My name is Yongjun. Yeah, hi, nice to meet you.
My name is Kwangmo Song. Nice to meet you too.
Awesome. So today we're going to talk about foundation models. And what we're going to do is we'll start by explaining what foundation models are, how you should think about them, why they are important. And then we'll go into some detailed examples of what it takes to train, fine-tune, deploy these models. And then finally, we'll hear from our friends at LG and some of the amazing work they've been doing with these foundation models. So let's get started. So you might have seen on Twitter recently, there was this pretty amazing, insane video that these two guys in Los Angeles made. And they basically took Stable Diffusion, which is a text-to-image model. So you give it a prompt of text, and it generates images. And they made this entire video out of it. So all they did was fine-tune it on a handful of samples, and they used text prompts, and then they got these incredible images and videos, and did bare minimum of post-production and any kind of traditional visual effects. And the result was something that you might expect from a professional studio that spends months of effort with top-tier teams, spending millions of dollars. And they maybe spent like a couple of $1,000 using Stable Diffusion, and they made something really amazing. So the question is, how did we get here? How do we get to a point where we could generate things like this from just nothing more than text? Now, one of my favorite XKCDs from about 8 years ago is this joke where someone asks the engineer, can you make me an app that tells you if a photo was taken inside a national park? And the developer goes, yeah, sure, no problem, that's easy. And then, can you also tell me if the photo contains a bird? And the punchline of the joke is, of the comic is that I'll need a research team in 5 years. And in 2014, this idea that you could just detect a bird inside a photo was a punchline. It was something that people just laughed about. And since then, we've just come such a long way. We've made so much progress in beating what we call human baselines. So there are different benchmarks for language, image, video, natural language understanding, different types of tasks that AI has become really good at. And what we like to see is, how have we gotten closer and closer to human baselines? So each of these lines represents a different type of benchmark that's used by researchers to measure the quality of an AI model. So for example, if you look at MNIST, that's a benchmark that sees if you can identify with AI human handwriting of characters, numbers, and so on. And with the MNIST data set, you can see that we made progress, but it took a while. It took almost a decade till we became as good as the average human. And then you see some benchmarks with ImageNet starting around 2008, 2009. And we got really good really fast. So almost about a year and a half after this comic came out, ImageNet was doing it. So what was the punchline of a joke in 2014 is probably a homework assignment in a CS class today. There's probably a workshop somewhere where you were being asked to do this in real time in like 30 minutes. And then if you look at the most recent benchmarks, the gray and the slightly orangish line at the end, it's almost vertical, the rate at which we're seeing these improvements. So the pace at which these models are getting better and they're able to achieve human baselines is accelerating. Now, how did this happen? One of the main things at work here is scaling laws. So the underlying AI models that were powering all of this increase in accuracy were becoming bigger, and they were training with more data, and they were using more compute. So on this graph, from this really interesting paper that I encourage you to read, it looked at the computing trend since the 1950s in AI. And what they found was that you can basically look at 3 different segments. So you see the initial segment till about 2008, and at that point, deep learning starts to really take off. And then you see another breakpoint right around 2015, 2016, when this era of really large models takes off. And the y-axis is looking at the number of floating point operations per second. So you can think of that as a proxy for how much compute do these models need. Now, what's interesting is that the rate at which researchers are finding new breakthrough models that are using more compute is increasing at about 10x every 10 months. So every 10 months, you get a model that's 10 times bigger, that's breaking some new barriers, doing significantly more impressive things. And if you look at some of the recent domains like text-to-image with stable diffusion that we saw at the beginning, that rate has actually increased even more, and it's now about every 2 to 3 months. So the scaling laws are what's powering these increases in accuracy. Now, when you make these models really big, that's when you get this concept of foundation models. So researchers at Stanford AI coined this term, foundation models, and it really took off. And the reason I personally like it as a phrase so much to describe these kind of models is they represent these very large corpuses of knowledge. So you're compressing lots of language data, lots of image data, lots of video, and you're able to create one very large model that you can then reuse across different domains, across different industries, and you don't need to keep training smaller separate models for every single thing. So if you look at examples like GPT-3 that some of you may have used, or DALL-E, Jurassic from AI21, OPT from Meta, Stable Diffusion and Stable Diffusion 2 from Stability AI, and Bloom from HuggingFace, these are all foundation models with tens or hundreds of billions of parameters, and they allow you to leverage what's already been trained on a very huge amount of data. So there are 3 ways in which you can interact with them. The first one is you could do inference with them. So you could say, here's the model. I will give it some prediction. I will give it some prompt and say, tell me what the capital of Spain is. And it'll give you a response back. You're not giving any new data to the model. You're not retraining or fine-tuning. You're just using the model as is. And sometimes, if you want to point the model in a particular direction, you can give it a few examples, what's called 0, 1, or few-shot learning during inference. So you can say, this is my question, or this is my prompt, and here's an example of the direction I want you to think in. You're not actually changing the model's parameters. You're just giving a few examples. The second is you can actually fine-tune and then deploy a customized model. So you can go and say, actually, my domain is unique. I have some custom vocabulary, and I'm going to fine-tune this model. And I will now change the model's parameters, and I'll deploy that into inference. And then the third one, which is really novel and interesting, and I think if we have the same conversation a year from now, I might actually just start with the third one, is reinforcement learning agents. So there's a trend where researchers are combining these very large language models with reinforcement learning agents that allow you to interact and make the model better. So the model gives some kind of generated text or image, and you say, I like that, I don't like that. And over time, it keeps taking that feedback and getting better. And this is a little bit more researchy. We'll talk about it in a minute. But these are 3 different ways. And the reason this is important is when you think about how you would leverage foundation models, you have to have some notion of what is the amount of expertise that your engineering and research team has to maybe fine-tune or retrain these. How much data do you have? And then what is the user interface with your end user that you're trying to serve these models to? So let's take a look at that. Now, there are 2 ways you can think about these different approaches. The first is you have the amount of expertise in custom data. That's one dimension. The second is, do you want to bring data to a model, or do you want to bring model to data? And I'll explain what that means in a second. So if we take the most traditional approach, you get some API from a company or a research institute that has a large model, and you call that API, you give it a prompt, it gives you a response back. That's the simplest. You have no infrastructure, you're not training anything, you're not changing the model's parameters. The downside is if you need to actually customize the model to improve accuracy, you can't do that. All you can do is hit this API, give it a prompt, get some response back. And then if you find that actually a few examples help the model get a lot better for your use case, there's no way for that API to actually have some memory or context of what worked last time. So each time you hit that API, you have to keep giving the same examples again and again, and you can't benefit from any kind of incremental learning or context that it might develop. The second approach is you fine-tune. So you say, I have 100 samples, 1,000 samples that really show what I want, and now I'm going to fine-tune this model. So I'll take the big pre-trained model, I'll fine-tune it, and then I'll deploy it in for inference, and it's more accurate for me. One benefit of this approach is that you can actually distill it. So you can make the size of the model smaller. And you can say, I don't need the network with 100 billion parameters. I know exactly what use case I have, so I can shrink and distill the model down. I can fine-tune with some data. And now that model becomes a lot cheaper for me to deploy into inference. And the latency gets better because it's a smaller model. The downside of this approach, though, is it requires you to have the expertise to be able to fine-tune. It requires you to have the data in order to fine-tune as well. And it also requires you to manage some of the computer infrastructure or use a service like SageMaker that allows you to trigger these fine-tuning jobs. And then finally, there's model drift. So let's say you use a Blue model or a Jurassic model from AI21 and you fine-tune it. And now you find that AI21 has version 2 of the model. But when you fine-tune on top of the version 2 model, something stops working. So you need to now repeat this entire process. So fine-tuning has a lot of potential, but the bar goes up a lot in order to making it work for you. Now the third one, which is novel and interesting, is reinforcement learning agents. So it's in a way combining the best of both worlds. So instead of bringing a lot of labeled data to a model and saying, let me train this model with my data, you're actually bringing the model to the data. And you're saying that this model already exists. Inside the model, in its latent space, it understands something about context, language, whatever specific domain you're looking at. And let me try and generate some content from it, and then let me give it some feedback. So you can have a human in the loop, which is just a way of saying someone, a guy who's like giving thumbs up, thumbs down as the model is making its predictions. Or you could have your end users give feedback. So imagine you're engaging with the chatbot, or you have some kind of generative image module within your app, and the developer makes that available to the end user tries it, and then gives some feedback in real time in the app, and that feeds back and makes the model better. So what's nice about this is you can scale the reinforcement learning aspect across your entire user base, across different segments of users, and you can keep making the model better. The downside is that it's relatively new. So it's more researchy at this point, it's less mature, but I think this is going to be a big area of development, and there's a signal that most of the large research organizations are now heading in that direction. And finally, you need more UI and product integration. So if you want to really leverage the reinforcement learning approach, you need to have something in your app that allows you to incorporate that feedback from users. Now, if we go back to the rate at which we're seeing the compute increase, the requirements increase, one of the things we've noticed is that hardware is getting better. So if you look at the generations of GPUs, we see that hardware performance has increased by 4x when you compare the V100 from Nvidia to the A100. And I think there's a similar 4 to 6x with the new H100s. The problem is that the GPU compute requirements for these state-of-the-art models increased by 1600x. And that leaves a big gap. So hardware is not going to keep up. You need software to optimize the performance of these models. And that's exactly where we've been investing a lot in AWS to develop the tools and the machine learning engines to train and serve these models efficiently. Now, to give you some examples of what this looks like, we do a lot of optimization to make all of these workloads run well on a single machine with GPUs and on multiple machines, so you can train in a distributed cluster. And our customers find this incredibly valuable because when you can utilize the underlying GPU and the network infrastructure better, you're able to train faster, which means your engineering velocity goes up, and you're able to train with less cost, which means that your overall bill goes down. In a very recent benchmark that we actually talked about today, Stability AI, which is the company behind Stable Diffusion, uses AWS now to train all of its foundation models. And what we found was that if we actually go and tune this algorithm and make the framework utilize our infrastructure, our network better, we can improve the performance, the training speed of the model by 58%. And in terms of how that can impact velocity, how that can impact the number of workloads you can run in parallel, it's really an order of magnitude shift for them. Because now they can have 2 different projects instead of 1 in the same cluster. They can finish those quickly, and then they can start 2 more, and so on. So the innovation flywheel just accelerates. And in addition to Stability AI, we also have a really exciting example that we'll talk about with LG. The last thing I'll just mention before we hand it over to Yongjun is that in addition to training, then there's a lot of optimizations you have to do for inference. So once you have these big models, you need to deploy them. So when that happens, you look at things like compilation, you look at the model servers, you look at ways to distill and quantize the model to make it fit on a GPU and run more efficiently. And then we're also investing in custom silicon like Trainium and Inferentia so that we can reduce the training cost while giving you better latency and higher throughput. So with that, let me hand it over to Yongjun to talk more about some detailed examples of how you can train these models.
Yeah.
Thank you.
Thank you, Aditya. Hi, good evening. My name is Yongjun Che. I'm an AI/ML expert SA in Korea SA team at AWS. I'm here to talk about how to train and host the foundation model in SageMaker. Let's get straight into it. To utilize the training environment, you first upload the train script for the foundation model to SageMaker Notebook, Amazon Code Commit, or GitHub. You then prepare a training container image with the packages in order to run the train script. When only installation of Python packages is required for training, we can use the SageMaker built-in container image. In this case, the packages are automatically installed when a training job is launched by adding the package's name in the requirement.txt file under the same directory of the train script. In addition, for the creation of a custom container image, the SageMaker built-in container image can be used as a base image. We can then simply write commands to Python or Linux package in Dockerfile. We are then able to use the custom container image after uploading it to the Amazon ECR, which is a fully managed container registry service. Lastly, dataset and pre-trained artifacts, such as pre-trained models and pre-trained tokenizers, are required. Such dataset and pre-trained artifacts are hundreds of gigabytes to the terabytes of dataset and pre-trained artifacts that need to be easily and quickly readable during the foundation model. And Amazon FSS for Lustre can do just that as a high-performance file system. Continuing on, leveraging these services to train the foundation model works well if we don't have enough infrastructure capabilities. To run hyperscale GPU clusters for the foundation model training, simply set the number and the type of instances to include clusters using Python code. And we are able to get the cluster we want and start the training right away. In other words, we don't have to set up networks or copy the training script for each instance in the clusters. This is because Amazon SageMaker training service provides GPU instances as well as fast network connectivity between the instances with the 400 Gbps GPU direct RDMA support on EFA. So as a data scientist, we only need to focus on preparing data set and training script to train the foundation model. Now, I'll introduce to the Bloom model. The Bloom model is one of the largest language models with up to 176 billion parameters. It is based on transformer and improved model performance by stacking multiple Bloom blocks, which have an attention mechanism and a multi-layer perceptron. Bloom model is commonly used for language generation, language translation, question answering, and more. We are able to use the HuggingFace to train the Bloom model. The HuggingFace makes it easy to leverage transcript, many data sets, and pre-trained artifacts for training the Bloom models. It automatically downloads them as soon as the training job runs after defining the dataset name, tokenized name, and Bloom model name to use. However, the largest Bloom model provides a sharded checkpoint, which is divided into 72 different files, and total download size is quite large, around 700 gigabytes. That's why it is recommended to download them in separate CPU instance using SageMaker Notebook or SageMaker Processing in a pre-processing step. And then we can save the train time and cost. It is better to save the result of the pre-processing step in FSS for Lustre and restore the saved file as a cache management or the load from disk method in HuggingFace. For example, when setting up the SageMaker training job, we are able to add the tokenized dataset and model weight path stored in FSS for Lustre, which will be used as an input to the Bloom model. It can also be used in transcript by defining the dataset and model weight path of the training container image in hyperparameters. When you want to train the foundation model with the SageMaker model parallel library using trainer class of a HuggingFace, we only need to add the distribution parameter when setting up the SageMaker training jobs. That's why SageMaker and HuggingFace are well integrated. We can easily train and host the HuggingFace model in SageMaker with model parallel libraries such as DeepSpeed, SageMaker model parallel library, etc. The parameter of pipeline parallelism and microbatch are required, and we are able to add tensor parallelism, distributed data parallelism, high precision, shared optimized status, if you want to use them. HuggingFace makes it easy to host the Bloom model in SageMaker using a trained model stored in Amazon S3. We can use the deep Java library container image provided by SageMaker to train a host foundation model. We can also write the inference script optionally to load and use the trained model for prediction. Compared to using DeepSpeed in benchmark test, we achieve higher throughput using SageMaker model parallel library. You can see on the table here, and we tested for 30 billion parameter GPT-2 model with the sequence ranks of the 512 and 2048. I'll then introduce to the other foundation models such as Stable Diffusion, VQGAN, and LBUS, which generate images based on the input text. In most cases, distributed data parallelism accelerates the process of training text and input image data. In addition, transcripts of these models are coded based on various frameworks such as TensorFlow, PyTorch, etc. As a PyTorch writing is currently one of the most widely used frameworks, I will explain more about the usage of SageMaker distributed data parallel library in PyTorch writing. Of course, we can use SageMaker to leverage various data distributed data parallel library in PyTorch writing. The use of the SageMaker distributed data parallel library when setting up the SageMaker training job simply requires defining the distribution parameter. Further, the DDP strategy of PyTorch writing in the training script is converted into the SageMaker distributed data parallel. When training the foundation model, resource bottleneck is the most commonly cited problem. Multiple cases have revealed immense needs for computing resources due to multiple configurations and or inefficiently coded transcript of the foundation models. If you look at resource bottleneck, we'll often see that the train speed may not be consistent in each train step, and CPU or system memory utilization is close to 100%. To address this resource problem, we can modify inefficiently source code in the data loader or add a specific configuration in Python packages such as OpenCV and Python image library. Also, it is effective to use Nvidia DALI in the data loader. Nvidia DALI reduced the CPU usage by processing part of the data loading on GPU instead of CPU. The Nvidia DALI requires a training pipeline to read and augment data. Then we have to learn the pipeline to feed the data through a data load iterator, like a DALI classification iterator. We found out that replacing the data load of PyTorch with the data iterator of the Nvidia DALI was able to mitigate the CPU bottleneck and increase the GPU utilization with the SageMaker distributed data parallel. Now, we are hearing more about a customer story for foundation models from a research scientist at the LG AI Research. Thank you.
Thank you, Youngjun. Hello, I'm Kwangmo Song, working as a research scientist at LG AI Research. Today, I would like to present about a case of our company. We have been using AWS service about a year and a half, and AWS SageMaker in particular has been very helpful in training foundation model with large-scale data. In the presentation, I would like to tell you about the features of AWS service we have been using so far and the trained foundation model using those features. First, let me give you a brief overview of our company. The official name of our company is LG AI Research. I'm sure some of you have already heard about the LG. In the LG group, there are several affiliates such as LG Chemistry, LG CNS, or LG Electronics. which is famous for its home appliances. The goal of our LG AI research is to solve problems and strengthen their competitiveness through the AI technology. We were launched about 2 years ago with the slogan, Advancing AI for a Better Life. Now let's take a closer look at what we do. Our job is to utilize the latest AI technology to help solve the difficult problem that our affiliates face. For example, we use AI for battery cycle forecasting and new drug development or vision inspection. This helps us significantly reduce the cost of manufacturing or service, and also allow us to work more efficiently. In addition to supporting our affiliates, we also conduct our own research. We present various research papers to the top-tier AI conference every year. And our current area of focus is the foundation model. The foundation model refers to a model that is pre-trained with a huge amount of data composed of various types of data, so that it can be used for various tasks with a little bit of fine-tuning. The foundation model is not only just a research topic, but a practical model that is expected to help our affiliates solve their various problems. The name of the model we developed is EXA1, which stands for Expert AI for Everyone. The idea behind EXA1 is to train a huge model using a variety of multimodal data, and then apply it to multiple downstream tasks in the form of an application. There are several applications we have in mind, but currently we are using text and image data for language processing, text-to-image generation, and image captioning. We trained the EXA model with 600 billion of text tokens and 250 million of images. However, we encountered some challenges while training a foundation model. First, because we use both text and image data, the size of the data set grows to hundreds of terabytes. So it has to be able to effectively manage such data. And also data input and output had to be done very quickly. In addition, in order to include such large amount of data in the model, the number of parameters of the model must also be very large. Therefore, it required a lot of resources, especially the GPU resources, that can be used with flexibility. And computation speed was also important for faster training. And lastly, we needed a small system to utilize and deploy the trained model to various downstream tasks for business fields. And in order to solve this problem, we initially thought about building an internal infrastructure. However, it was estimated that infrastructure maintenance team of about 20 people would be needed to purchase, set up, and maintain the GPUs. Therefore, significant initial cost would be needed. In addition, since a new GPU is released approximately every year, we determined that there is a problem in purchasing it every time. And we also needed elasticity to use more GPU during certain periods of time. Then we started looking into AWS for health and were be able to solve these problems using their solutions. For example, we use AWS's FX for Lustre to manage data and allow faster data input, output during the model training. SageMaker also enabled us to try distributed training in very large scale. We were able to adjust the number of instances and experiment with the just right number of GPU as we needed. The computational speed was also significantly improved by using the SageMaker data parallel feature. And lastly, the EC2 instance made it easy to inference and fine-tune our model. In particular, being able to access these solutions without much difficulty was the biggest advantage for us. The schematic diagram looks like this. SageMaker operates in the same way as Youngjun from AWS explained earlier. And what the user needs to do is very simple. First, put the data to be trained into an S3 bucket, and then sync it with FXX for Lustre. The linked file system of FXX for Lustre is connected to its instance and provides the training data very quickly. And after slightly modifying the code used in the local environment to fit the SageMaker environment, you can proceed with SageMaker training through a Jupyter notebook. And the generated model is saved in S3 bucket and can be easily retrieved through EC2 instance for fine-tuning and inference work. So as I just mentioned, that the training code needs to be slightly modified to fit the SageMaker environment. The same goes for SageMaker data parallel. This is code that applies SageMaker data parallel instead of the existing PyTorch distributed data parallel. Just add a few simple lines and you will see the job done. And the applied SageMaker data parallel is much faster compared to the existing PyTorch distributed data parallel. Of course, the amount of performance improvement varies depending on training environment or the number of GPUs. But in our case, when using SageMaker data parallel, we were able to train about 10,000 iterations per day. This is about 60% faster than the 6,300 iterations we recorded when using PyTorch distributed data parallel. The time required to train one epoch was also greatly reduced, and resulting in a cost saving of about $70,000. This is how AWS SageMaker enabled us to train the model more simply and quickly. From here, I will show you the experimental result of our trained model. First up is the image captioning task, which automatically creates a corresponding caption from the input image. Whereas conventional model generates a short sentence caption for input image, but our model describes the input image in very detail. You can also tweak this a bit to generate related keywords rather than sentences. If you provide an image, it will generate several appropriate keywords, such as in hashtag forms. Next is the image generation model. This is a field that has been receiving a lot of attention since OpenAI's DALL-E research. When the user enters the desired sentence, the corresponding image is generated. The model does not simply search for images that correspond to the text, but understands and creates them. For example, in the case of a pumpkin-shaped hat, the corresponding object is not in the data, but the model understands and combines the property of each object to generate a new object. And fine-tuning this model enables various tasks. First, you can upscale a small-sized image to a high-resolution image by applying it to the image super-resolution task. You can also modify the image by using image control task. Let's say that you request to create a new object for the masked area. A real flower is created next to the bed, and a painting of a flower is created above the bed in a style that goes well with the surrounding wall. In addition, you can just change the color of an object without changing the shape of an object. And it is also possible to give prior knowledge about the image region. If you give the model an input to use the segmentation information to generate an image corresponding to the sentence "surfer standing on the beach," the model creates an image that fits the region and text. Okay, so we were amazed at how easily we can use AWS features for diverse purposes. They enabled us to train our model effectively. We were particularly impressed with the scalable use of multiple GPUs with SageMaker and the significant increase in training speed using their SageMaker data parallel feature. And the AWS team helps a lot to troubleshooting several issues. We hope to continue this kind of collaboration. And we plan to use SageMaker's model parallel feature to further increase the size of our model and train more efficiently. We are also willing to leverage SageMaker's inference feature for a more effective model management and deployment. Okay, thank you for listening.